And this is part 3 of the lecture on ecosystem diversity and change. We will be looking at the effects of climate change and changes in geology on evolution and extinction. So in 4.3, one of the things that we're going to start out by looking at is how the tectonic plates move. Remember that we've already discussed tectonic motion. It was chapter 14 and we covered it in unit 1. The tectonic plates affect evolution and the location of life on Earth because of continental drift. Now, not only will that change the climate as one continent moves from, let's say, equatorial to a more southern location, as is the case with Antarctica, that will help determine what types of life are able to survive. Species are also able to move and adapt. They can go to new continents, and then when those new continents are separated through tectonic motion, they will change and become two genetically different species. But another thing that's not even mentioned here is that throughout time, the plates have not only drifted apart, but they have also drifted together. And we actually believe that one of the most extensive extinction events on Earth, the Permian extinction, which killed a majority of the marine species, we believe that the reason for that was the continents coming together to form Pangaea, and so they simply squeezed out the ability for those species to survive in what had been productive coastal areas. Earthquakes can also affect a population because they will isolate a population. And if you have one species on one side of an impassable crack and another part of the same population on the other side, well, they will eventually diverge and become two separate species. Volcanic eruptions, that's another way that we can destroy habitat, wipe out species, or you could also perhaps, depending on the type of volcanic eruption, you could separate the species entirely if they are unable to cross the chasm that has been created by the caldera. So looking at the movement of the plates of Earth, you can see Pangaea 225 million years ago. Then you see 135 million years ago, we've broken up into Laurasia and Gondwanaland. 65 million years ago, we had essentially distinct continents. You can definitely see where they have moved. And you can see that North America, Eurasia, Africa, those are still very much connected, as are Africa and South America. This is around the age of the dinosaurs, and this is also supported by fossil evidence where we have some of the same dinosaur types along those boundaries. And then present day, you can see where the continents have moved to, and you can also tell that India is moving very, very fast in comparison to the others. So when we look at the original size of India and where it is today, that's the reason for the Himalayas. So we're sort of bringing those two units together here and looking at this. And this animation is going to show you that continental drift. Now, not only are we currently undergoing a climate change, but we've undergone climate changes before, and when this happens, we affect natural selection. Ice ages are followed by warming temperatures. We can think of the organisms that we know were present in the last ice age, like the woolly mammoth, the saber-toothed tiger, and we can look and see where those modern descendants are today. And obviously there's been a change in the species. They have been through natural selection. The fittest species survived during the Ice Age by having thick fur, but now those most fit species do not have the thick fur. So we can obviously tell the similarities between a woolly mammoth and a modern day elephant, but they have been specially selected for the current environmental conditions. But it's interesting to note that you then still have the genetic markers in there somewhere for extra hair growth on an elephant. And so there is a possibility that were we to enter another ice age, we would start to see the elephants look more and more like a mammoth had looked. Again, we're talking about speciation, though. It would take hundreds of thousands, maybe even millions of years based on the gestation and the generation times for elephants. The next factor is collision between the Earth and large asteroids. So this is, again, what we still presume is the reason for the disappearance of the dinosaurs. Why this is so important is as a dominant species is pushed out of the way, new species are able to fill those niches, or new species are able, or old species are able to specialize more. And so again, this is that idea of niche, breadth, generalists and specialists, and how they come to occupy the different niches. If they had been outcompeted by a dinosaur species, as we believe the mammals were, then once the dinosaurs were out of the picture, those small mammals got to really explore the possibilities of their new niches. And now we are in the dominated era for mammals. So again, anytime we've got extinction, we've got the possibility, the window is open for new species to come in through speciation from existing species. And here we're looking at changes in ice coverage in the northern hemisphere during the last 18,000 years. And so you see modern day over here on the right side. Ice coverage is pretty minimal. We have ice coverage here in Greenland. We're only looking at the northern hemisphere. This right here is sea ice. We're not going to count that because species are still able to really live underneath. But if we look here back in the Ice Age, you can see where continental ice coverage had persisted. You also see that the land above sea level was very, very different. And so this is just an idea of how climate change can change land availability, can also change, obviously, the temperatures and what species are able then to survive. And that's the end of part 3.